Alright, so we're going to pick this up with a discussion of type checking. And our first point of discussion here is this distinction between static and dynamic type checking. Right? So static type checking is what we have in languages like ML and Java and Pascal and C. The compiler does this checking at compile time and gives us errors when we compile our program. Dynamic type checking happens at runtime. So this is commonly done in interpreted languages like Python or scripting languages or Scheme, where we don't get any error messages about type errors until we run the program. And so that leads to a couple problems with dynamic type checking, right? So think for a minute, what can go wrong here? What is it that we may not appreciate or may not like about dynamic type checking? Well, one thing is the errors are reported too late. Right, my program's already running and I find out there's a bug. So this is, if we ship our code, it's running in production and a type error happens, then the user sees this instead of the developer. So this is certainly a problem. Rigorous testing is something that can address this. Some argue that with lots of unit tests, all these sorts of type errors get sorted out along with other logical errors, and so dynamic type checking is not a problem in that sense. That reporting errors at runtime is not a big deal if we find them all with testing. Another problem, however, is that the code is too slow. Right, every time we do an operation, we have to check if the types are correct. So if I have two numbers and I want to add them together, we don't just make use of that machine instruction to add two numbers. We have to first inspect some tag on the types to see if they're both numbers, and if they are, we can do the addition. Otherwise, we raise an exception or otherwise terminate the program. So this sort of code is just terribly slow if we do anything that's sort of numerical, and thus, well, it's too slow. So, right, it's a bad thing. All right. So we have another notion which is called strong typing. Right? And so we might ask ourselves, well, how good is the type checker? Right? The standard ML type checker doesn't let any type errors get through, where we saw with variant records in C and Pascal that we could still have runtime type errors even though the compiler was happy enough with our code and didn't report any errors at compile time. So we say that a type system is strong if it only accepts safe programs, right? So what is a safe program? Right, so type safety here, we say this is a property of a program, not a language. And a program is type safe if it always executes without any type errors, right? So regardless of the input, it always executes without type errors. So we can write type safe programs in Python or machine code. We just have to be more careful because those languages don't check that for us. Where a language like standard ML, its type checker will ensure that any program it compiles and runs will not have any type errors. And so a type system is strong if that's what it does, right? So this is a property of the type system of a language, where type safe, right? We also have this notion this is a property of a program. All right, so these sort of strong type systems are able to assign a type to all expressions in a program at compile time. Right, so a type system, if it's not strong, it's weak. So we think of C and Pascal as languages that have weak type systems. So they allow some type errors to slip through. All right, so one thing that's interesting here is that a strong type system will necessarily reject some type safe programs. Right? We can't know everything that's going to happen at runtime. Right? So you may consider a program if foo ABC here is our condition, and if this turns out to be true, then we'll have our integer x declared here, x set equal to 6. Else x set equal to hello. Alright, so a strong static type system will reject this program because there's a possibility that we're going to assign x the string value when it's declared as an integer. But of course it's possible that foo always returns true, and so thus we would never execute the else branch. Right? So this may be a program that is type safe and that it would never run and cause any runtime type errors, but we can't know that at type checking time, at compile time, and thus we would reject this program. Right? Sometimes this can be a problem. Right? If you think back to the earlier days of Java, Java 1.4, or what we have in C, is that we try and write generic lists or generic sets or generic trees, any sort of container type that we want to store different kinds of values in. This becomes something we can't do in a type-safe way. So in Java 1.4, we could create a list, and all the elements were of type object. So this was something we had to deal with so that we never really know what's inside that list. Same thing with void pointers in C. All right, so when generics came along in Java 1.5, that fixed the problem. But otherwise, we had these sort of complicated encodings that, well, essentially lead to a loss of type safety, in that we have to downcast from object down to some particular type we expect it to be, but we don't necessarily know that's the case at compile time. All right, so what is it that people do in programming languages that work on type systems? Right? The nature of this work is that we want to preserve strong typing. So if we have a strong type system, we don't want to break it, but we'd like to make it accept more good programs. Right? So maybe there's some analysis we can do that will cause it to accept programs that are type safe that it would have otherwise rejected. So a big step forward here was this advent of parametric polymorphism. And so that's what we'll turn to next.